Hey, advanced algebra, the last section, last couple days of this class. How cool is this? We're looking at domain and range. We're going to review the whole just say no idea and then unusual proofs and read the domain and the range from a graph. So here we always said just say no to three things. What are those three things? See if you remember. But if you had the PowerPoint in front of you, you knew already. Just say no to zeros in the denominator, negatives in an even root. Let's stay real. We did look at complex numbers and imaginary numbers, but let's keep the numbers real. And what's the third? Drugs. Yes, sirree, Bob, gotta say that. Okay. You'll need to know interval and set notation, which we've now covered thoroughly, but I understand you guys know well anyway, and be able to use the one that's most appropriate, that works best. So here are a couple examples from the first situation where we just say no to zeros in the denominator. So state the domain, and the technique is to establish or identify what x cannot be. So in this case, it made sense to use set notation. So we use set notation, and notice I didn't say x member set of real numbers. Remember, if you don't specify, it's assumed that we're talking about real numbers. So whenever there's a zero in the denominator, even if you could cancel it and cancel it completely, we couldn't necessarily cancel it completely here, but you don't ever want a zero in the denominator. Here's some more examples of the second kind. Find the domain of each, and then in this strategy, you identify what x must be. And here I always do graph notation to verify we're okay with this. And then there's interval notation. Notice that it's really easy to transfer this into set notation by just saying x such that and putting little braces around in both cases. Now, I usually like using less than sign, so this isn't traditionally how I like to do the set notation, just because it's nice to go in order smaller to larger numbers. So let's check out this proof. If we start with x equals y, I can use the multiplication property of equality by multiplying both sides by 2. I can then, if x equals y, I can subtract the same value from both sides of the equation. I can subtract x from this side and y from this side. I'm subtracting the same value. Then I can subtract 2y from both sides, add x to both sides, and then factor, and now divide through by x minus y. And what do I get? And explain what's going on here. So yeah, 2 equals 1. You just proved that 2 equals 1. What is going on? Does anybody see it? I tell you, it's all fun and games until someone divides by 0. Okay, don't divide by 0. That you get this whole set of things. We always say you've got to have, if you ever want to divide by 0, you got to have Chuck Norris in the room. So there's a whole set of really fun, some of you just divided by 0. Okay, so yeah, all these crazy things start happening like 2 equals 1 when you divide through by 0. Where did we divide through by 0? See if x equals y, when you went from here, you divided by 0 right here. Lots of bad things happen. Sometimes 0 is incognito, so be careful of that. Here's another proof of 2 equals 1. See if you can find the place where, I betcha we divided by 0 here. See if you can find that place. There it is. Hope you found it. And if we consider this function, we might say, okay, that x minus 4 over x minus 4 equals 1, so we can consider this equal to x plus 5. How do you deal with that? This function is not the same as that. It's got one little difference, and that's at the value of x equals 4. How is it different? Well, let's start by graphing y equals x plus 5. So there's the graph of y equals x plus 5. But if I want to graph the original function, 4 is outside the domain, and I have something called, literally this is what it's called, a hole in the graph, or a removable discontinuity. So if I want to graph the original function, I'll put a hole in the graph, and I know that point is 4, 9. So I'm going to adjust this and say this is equal to x 4 over x minus 4. There's the original, there's a graph of the original function with x minus 4 over x minus 4 in there. Another thing we did earlier was we were solving rational equations. We worked with rational functions. And so solve this equation. Find the lowest common denominator, combine terms, find solutions for x, and then come back on when you're done. Here's the first. I showed most of my work here, not quite all of my work, but most of my work. And then I get the end. The last thing you have to be sure to do is check your answers. You need to hold on what the domain is, and you can see that this is an extraneous solution, and we only have one answer. Try that. If you missed that last time, here's another one for you to try, but always check your domain. Always check your answers, too. So yeah, there's no solutions to this here. Now, the all-important just say no. It's important, so we've reviewed it twice, was the first of 3 techniques. And the second technique is finding domain. And now we're going to find range too, the set of possible y values considered graphically. Now let's look at this. This is a circle. It looks like the center of the circle as at 5, 4. See if you can find what the radius is. And first, find the equation of that circle. I hope you remembered what the equation of the circle was, but just as a review, there's moved 5 to the right, 4 up, 4 up, and the radius is 3. So using this graph, we can look at this and determine what x values are possible, what x values fall somewhere on the circle. There are some that don't. So we might be able to say the smallest x value is here at 2. Where's the largest x value? Use interval notation to determine that. Then do the same thing for y. What's the smallest y value? And then what's the largest y value? See if you can find the set of possible y values, and that will be the range. And the easiest way of doing this is indeed reading from the graph. It's a little bit trickier to do this arithmetically or algebraically from that equation. And we could express the domain and range in either interval notation or in set notation. Do remember, if you use set notation, use the y for the range. Reading the domain and range from a graph is a really important skill. So part of what we want to do here is establish what the coordinates of the points are, and then find the set of possible x and y values for this. Now, so I want you to try all 3 of these, but let me point out that, yeah, there are specific points given to you here for this pink squiggle. And here we've got the vertex of this parabola. When you see an illustration like this, it is assumed that that continues going up and up and up and up infinitely and flaring out infinitely. So let's look at these three functions and their domain and range. For the first, notice I gave just the x values. The lowest x value, even though it's a point way high above, the y value is bigger. Go from the lowest x value to the highest x value, and then the y values is the range, the lowest y value to the highest y value. When we have a negative slope, it looks kind of tricky. So for this parabola, opens upward, the domain is all real numbers, and I could just say that. Range is if I want to put it in set notation. That actually would be really nice. I'll put it in set notation, and then the range is -3 to infinity. It's -3 up above. So this point right here, the 1, 7, may have been tough for you to read. I counted because I thought, ooh, I can't read that. So you do want to be sure your scale is correct. That's why I've got these guys circled here. So I want to be sure my scale is good before I assign values. So my domain, let's start there, -4 to 7. And this -4 is this lowest x. I'm reading left to right. And then the x value that's the highest is a 7. Notice I'm excluding it because it's an open hole. For the y values, the range, -1 down here. If I read from down below to up above, -1 to 7, I exclude the -1. So here's one that's a little bit trickier because you've got this hole in the graph, and there is no y value at 1. So how would you represent the domain and range here? And for the domain, notice you've got no -2. So be sure, I'd recommend use interval notation and establish the domain and range. So, okay, notice this is how I've eliminated the -2 from the domain. Domain's a little bit easier. For the range, it gets tricky. You want to go from -2 And then notice here you might be tempted to do something at the y value of 0, but you do have y values between 0 and 1 right there. Those are y values between 0 and 1, aren't they? And then so you really just want to exclude the 1 up until 4. That's the y value is 4. And so you want to include that 4 at the end. Let's include that 4 right there. So let's fix that, and then let's look at the next. This one was so good, I just have to show it again. Third technique is using your brain, particularly when you have a word problem, a real world problem. For example, when we had the open top box problem, do you remember we cut the corners out of cut squares out of the corners of a piece of paper? There was the domain we talked about. X couldn't be negative and X couldn't be too big, because then you couldn't cut squares out of the side of the box. So we had to use our thinking skills. Same kind of problem happens when you're measuring the height of a baseball after somebody's hit it with the bat. You can't take the time before it gets hit by the bat, and you can't take the time after it hits the ground to model that with a parabola. You've got to limit the domain. And then also the range, the y values, the height with the bat example, or the volume of the box is going to be limited as well. Let's explore this. See if you can figure out what the domain and range would be of this situation, a 21 by 27 piece of paper with squares removed. Yeah, I had to do a little bit more work for this one. So the volume of the box, I couldn't have X bigger than 10.5, or I couldn't cut 2 squares out of the corners. And then to find the range, I had to graph it and find the maximum value. So yeah, I did plug that equation in my calculator and find the max value there. So that's how I did that. It took a little more work than maybe you thought. Now, this is a page from a homework assignment, and it's looking like it didn't copy very well. But should you have problems like this where you need to establish the domain and range, remember the domain is the set of X values, or the first values, and the range is the set of Y values. So if you have this kind of picture, this is your domain, the first values. They drew arrows then to the range. So these values are the range, and these values are the domain. If you're given a set of, or a table here, the first values, the independent variable is the X, and the other variable, the dependent variable, is the Y. So if you're given coordinates of points, again, the domain is the first value, the range is the second. These sets are very, very limited, so the domain may be just a couple points that you list using set notation. There's your domain and range. Your homework is actually a little better. That print didn't come out pretty well, so I actually made out a little worksheet for you on this. Now remember, domain is the set of first values, range is the next. You're literally just going to list them. The set of X values for number 1, you're just looking at, literally, you just want to list 2, -5, and 12 is your domain. Just the list of those 3 numbers, for example. These are different ways of representing X and Y. You just want to list those values. Here in a graph is where it becomes more infinite values, and you really want to use interval notation for these if possible. Sometimes set notation is nice too. So this is your homework. There is an answer key. I think there's a second page here. There's more graphs. There's a couple of think problems, and some of the think problems at the end. Oh, look, there's the beloved box problem. Some of the think problems are more challenging. There is an answer key posted online. Have fun with this. Ask questions if you need any help.